Just a minute. I'll allow the mic also. Just wait. I've allowed the mic, so ensure that no one opens their mic unless required. We'll wait for others to join. Okay. I hope my voice is coming.
Yes, sir. Your voice is audible
Thank
here.
you. Yeah, thank you. Let me share the screen. I'm sure you would be able to see my screen, right?
Yes, sir.
Uh, what is the official time? Is it 10:40 or 10:30? Oh,
10:30.
thank goodness.
10:30.
13,
3 more
yeah.
minutes.
Mm, okay. Very few of you have joined today.
Previous session is still going on for maths, so I guess they will be joining.
Okay, so you have a session which is going on. Okay. So if I'm not mistaken, we'll do a quick recap, right? So that by then people would start joining in. Uh, that way they're not going to, yeah. So in the previous sessions, we were actually uh, covering the perceptron part, yeah, if you remember. And we talked about perceptron, we talked about how a biological neuron works, and we talked about the 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 mathematical model of a artificial neural network, right? Isn't it? So in a way, we understood how a basic unit in the neural network works. That is the neuron, right? Then what we did is we then touched upon the most popular and the first actual neural network that came into existence. That was the perceptron, right, in 1958. Then we also talked about, so we talked about the entire mathematical representation of the perceptron. We talked about the usage of bias and all those things, learning rate. So these are some of the parameters which are important. And then eventually what we did is we started using the perceptron for solving simple problems like logic gates. Still, we were using the a single layer perceptron, right? A very simple perceptron that was able to solve problems that can be linearly separable, right? So we talked about this. We understood how a perceptron learning algorithm can be written and can be understood. Then eventually what we did is we solved some of the very basic gate problems, gate functions, right? And we saw that how a simple perceptron would be able to do a learning, right? So this was the first ever kind of learning algorithm that you built in, right? And how it is able to solve that particular problem using multiple epochs, iterations that we saw. We talked about AND gate also, similar kind of thought process, right? And then we eventually ended our session by talking about that why a single perceptron would not be able to solve a XOR problem because these were the two kind of contradictory statements that it has, and this is the exact output that is required in the XOR function. So I cannot draw a single line for this particular example here, over here. So obviously these are two classes, red and blue, suppose. So by drawing a single line, I cannot separate both of my classes, right? So either I need two linear lines in order to separate it. So obviously, as a single layer perceptron is able to separate your classes by drawing a single line that we understood, right? So that is where we would take up this problem XOR, and then we would try to see how we can use something called multi-layer perceptron now rather than a single layer perceptron. So by using a single layer, I was not able to solve even a simple problem like XOR. So we would now in a session would shift our attention towards multi-layer perceptron. As the name indicates, there would be not a single layer, there would be more than one layer of, so introduction of hidden layer would come into existence. The same thing that we talked about in the initial session. So this was the issue, right? We also tried to solve the same XOR problem with the single perceptron. So this kind of scenario came into being where the weights, we started with some weights and it eventually came out to be zero. So the learning eventually went to zero. So obviously it eventually means that there's no learning, right? So we talked about why it failed, right? And convergence of perceptron learning algorithm, what it means, we talked about, right? So, I mean, in a way, you understood that how we can use perceptron to solve simple problems, and also how we cannot use perceptron to solve another simple problem that requires, say, suppose two separators or maybe other kind of method to separate the boundaries, right? So, I mean, we would come back to, yeah, we started talking about non-linearly separable data. Are we, everyone on the line, on the same page?
Yes, sir.
Yeah,
Yes, sir.
yeah, yes. So we will be focusing on non-separable data. We started with this particular session actually. So these are some of the examples. If we just focus on the data points, the visualization of these data points. So obviously in any of these cases, I cannot draw a single line to separate the data. And that is where a technical solution to these problems, looking at a solution, is that can we throw these data points, or when can we transform these data points in a higher dimensions or into another representation? That means transformation of say suppose this representation of data into another representation, we normally call it into higher dimensions, right? So that in that higher dimensions, I might see these data points in such a manner the way I see in 2D space. So I may see that these data points might accumulate somewhere here, and these green data points might accumulate somewhere here in higher dimension. And then in higher dimension, I can separate these by drawing a separator line by using a simple thought process that we were using earlier, right? So the entire thought process now would shift towards uh, representing these data points into or transforming the representation of these data points into another representation, and technically we say that representing the data points into higher dimensions, right? So the entire thought process would lie upon that. So we did talked about, so before we can apply this, we talked about what is multi-layer perceptron. We talked about the components of multi-layer perceptron. It might look like this, where you can see the introduction of hidden layer might come in. So the word multi can refer to even a single hidden layer is introduced. It would come on the category of multiple layer, hidden layer, multiple layer perceptron, right? So they can be in very complex networks. These hidden layers can be thousands of hidden layers might be introduced, right? So this is a typical multi-layer perceptron example where you would find input layer, right? Input layer is this. I always told you that input, we normally call it as a layer, but actually it is not a layer. It is just the input, right? And so this is basically a three layer network. So two from the hidden side and one from the output layer, right? So we would have hidden layers, we would have output layers. And then this was the mechanism that we also started with. So there would be a forward propagation. Forward propagation means what over here? That we would start calculating when the input would pass on to the hidden layer. So how the calculations would be done at the hidden layer. So once the calculations at the hidden layer would be calculated, you know, the methodology would remain same, right? That is the activation functions, right? We would use the weighted combination of the input and the output, right? So obviously we would calculate these outputs, right, of these neurons first. So we moved from here to here, and then similarly once this would get calculated, we would calculate this and we would calculate the output of these neurons, right? So again we are moving towards in a forward fashion, and once this is calculated, we would now eventually calculate the output for these, right? Output layer, right? So, so I mean, the direction, if you can see, it is moving from left to right in a forward direction, right? So that is the reason we normally call it as what? The forward propagation. So once we would calculate certain outputs, say suppose alpha and beta, whatever, right? So obviously there would have been some known values or the target values of these. So there would have been a target value alpha and beta dash, for example. So these were the target values, these were the calculated values. So I'll call it y dash and suppose this is called y. So there would be some kind of error. Obviously, I cannot achieve the target values in a single iteration, for example. So obviously, now the question would be how to deal this error, right? How we would use this error, we would calculate this error, and then using the knowledge of this error, I would try to update all my weights in a back propagation manner. I mean, I would first update the weights which are between output layer and the second hidden layer, right? Then I would update my weights between the two hidden layers. Then I would update the weights between the input and the first hidden layer. So now the propagation or the back propagation of error would happen in a backward direction, right? We would understand this. This particular thought process of back propagation would come into session 4, but I'll give you an idea, right? Before we can actually jump to session 4 whenever it comes, right? So so there would be a concept of back propagation. I also talked about error calculation. That is the loss function. We would represent that error using some function. There has to be some function through which I can represent this error. So that function we would call as the loss function. then how this error or the loss function would get propagated in order to update my previous weights. Why I needed a update on previous weights? Because I could not achieve the target learning. So I need to update my learning in a similar way we do, right? If we wanted to learn something and we're not able to learn it, then we do update our learning. And in every updation, the idea is to reach towards the target learning, isn't it? So in order to do so, these are three typical steps. Then in order to do these things, it may happen that in spite of formulation, in spite of following a proper methodology, I may not reach towards my learning or the target learning, or it might take too much of time. It might be very time consuming aspect. So that is where the introduction of optimization algorithms or optimization techniques would come into play, so that I can reach towards my target learning in a lesser number of steps in a way, right? So that is where optimization algorithms would come into play, right? Or eventually you can say that how I can reach towards my target learning, what the algorithm I want to follow, that would be told by these optimization algorithms. Okay, so I did little bit talked about what exactly these hidden layers actually are doing, right? So I told you in a very simple sense, these hidden layers, there's a transform of the data in one form into another form, right? Why we need it? Because with the original form, I was not able to separate my data. So I would definitely try and to dig into more into my data, would try to get a different representation so that eventually I can understand or my target was to separate the data, right? So as of now, we are only talking about separation of my the eventually the classes or the different kind of data that I have. So right now, our thought process is only on two classes, for example, right? So each hidden layer would create in a way new features also. When I say that into another representations or the intermediate representations, so these intermediate representation in a way can be understood as kind of creation of new features or intermediate features, right? So these hidden layers would enable the desired learning rates, because by one transformation to another transformation, I may find some kind of answers. So what I've written is that they don't pass input forward, they convert the raw inputs into a better representations, right? So I mean, this can be a typical way of writing the hidden layer. For example, if I talk about this hidden layer, right? So this hidden layer can be, right? It might, so I might look this into, for example, this is your input one, this is suppose input two, right? This is, I'll call it suppose x1, this I call it suppose x2, right? So I may have hidden layer, for example, one and two, for example, right? And I'm just using a very simple connections between the two. And suppose this is an output layer, right? This is simple. So this is one hidden layer has been, so I'll call it suppose H1 over here, and I can call this as an H2 suppose. So H1, and this is suppose W1, this is suppose W11, sorry, this would be W22, for example. Similarly, this would be W12, and this would be W121, for example, right? So if you can see, H1 is nothing but W11 into X1, and W12, this is W12, right? This particular, and into X2. So, and I hope there's a bias that we have already talked. So there's good bias value associated with the hidden layer. Bias values are never associated with the input layers. Always remember that. They always get associated with the hidden layer and the output layer. So there would be bias value associated with this particular H1. There would be another bias value, suppose B2, which would be associated with, say, suppose H2. And then eventually this is Y. So once I'll calculate H1, H2. So what is I'm trying to show here is the forward bias. So Y would get calculated similarly. So there would be a function. So this is suppose this weight is suppose V1 and V2 suppose. So V1 into H1, we have already calculated H1. So in a way, what we have done is we are calculating the output in a forward bias fashion. When the forward bias is done, then we would compute the error. error between what? The target value and the value that we have achieved, after computation of the output units. Then how I would use this function could have been a very different manners. It could be treated and it could be discussed in many different ways. Are you able to hear me, everyone?
Yes, sir.
Yeah, perfect. So
Yes, sir.
this is what we will discuss about, that why I'm using these kind of errors, that would come eventually into our discussions later on. Right now, you can see that we have used the squared error. So eventually, some question might come into your mind, but we will talk about these loss functions separately, right? So we have taken the squared error over here, right? I could have simply taken t minus of 1, yeah, isn't it? And I could have taken the absolute value of t minus of 1, right? Whereas the most common ones are where we take the squared functions. Anyway, we'll come to that later on. And once this error gets calculated, now we thought process would be how to throw this error, or how to use this error so that the 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 previous weight values can be updated in a way so that next time when I'll do a forward bias in the second iteration, the difference between the t minus of 1 can be reduced further. And this would eventually go on till to a stage where I would declare that my output y is very close to t, or in ideal condition it is becoming 0, right? Or where I can say that the learning has stopped in a way, right? So the backward phase would start beginning, right? The error is back propagated to adjust each weight. When I say each weight, so all the weights will participate, right? Necessarily it is not important that all the weights would participate. We'll throw a discussion about this later on. It's not the right time. So the output weights are updated to reduce the final errors. Hidden layer weights are updated. The weights between the input and the hidden layers would get updated. So all the weights would get updated, and this iterative refinement would keep on going. I told you till I I'm able to achieve a desired error, or say suppose if 5% of error is something which I desire, for example, because technically in numerical perspectives you would never see a scenario where t minus of y is always 0, right? So transformation means I've told you that this could be the raw data. For example, I started with x1, x2, right? My transformation by using these hidden layers might convert a scenario like this. So marks and interview score might now can be interpreted through hidden layers in the form of confidence score, skill strength, risk level. So this might be more useful as compared to marks and interview score, because I could not see much interpretation from these two inputs. So the interpretation of confidence score, skill strength, and risk level might be more useful, which got converted, or which got highlighted through hidden layers, right? So why this is important, I told you, because the real world is messy. I'll call this as a real data. So this real data can be messy. I'm not able to understand it properly, not easily separable. So hidden layer does what? So these kind of typical tasks that hidden layers might do: reshape your data, stretch your data, rotate it, separate it, if someone asks you, right? There's a typical example of what a hidden layer can actually do. Hidden layer will convert the raw input data into a smarter form, or another representation where the layers, or where the patterns becomes visible, right? Anyway, so I mean, this is what I've already explained, that what exactly hidden layers would actually be cumulated with. So we, as I've told you, the activation functions always come into play. So we would cover upon the activation functions also today. Some of the common activation functions I would definitely cover today, right? So this is can be very simple representation, that what we did, one form got represented into another form. So although we do not get these kind of representations by just applying one hidden layer, it might take multiple hidden layers. So one of representations, from the starting representations, we got a conversion into another representations, where I can now separate my data in by separating line, right? So this could be the initial form of the representation of the input data. This could be the intermediate representation. Then ultimately you can see that after one more introduction, I was able to represent it by drawing a single line. Okay, little bit on the some of the advantages of NMLP, right? And then we will pick up the XOR problem. Then we will see that how we can use the MLP to solve the XOR problem. So in a very typical manner, MLP are versatile. They are able to introduce non-linearity, and they're scalable also. That's the beautiful part, right? So the versatility means that we can use these MLPs not only for regression tasks, and we would do this task, right? We would do both these tasks. So we can use these MLPs for both classification and regression tasks. I hope you have little bit of an idea about classification and regression. I'll quickly give an idea. So regression is, for example, you have the height and the weight of a person. So regression would talk about the relationship between the two variables in a way that what is the relationship between the height and the weight of the person, and by studying the height and the weight of the some set of training examples, can I predict the weight of the person given the height of the person, or a vice versa. But can I predict the value? So here in regression, we predict the value, right? On the other form, regression is a kind of classification only. On the other hand, classification is what? Classification talks about that we would talk about the classes. We would separate the classes. So I would draw a line so that I can separate the classes in two kind of classes. Suppose male or female, for example, right? Or anything. So the classes would be known to us, right? So they would not talk in terms of values. So we would not predict the values. Here we actually predict the classes. So that's the difference, right? So maybe in the next session we would be, in fact, this session only, I think we should be able to start with the regression task. Non-linearity, I've told you, that is the basic purpose of MLP, right? We talked about this. Scalability is a beautiful feature, right? I mean, once we're able to develop this network, so it becomes scalable. I mean, with more and more data, I can increase this network size and all those. I can increase more GPUs or more hidden layers. So, I mean, I can increase the network size, and I can it can be very well mapped with the architecture through hardware level, right? So that is the beautiful part about neural networks. So a lot of scope for parallelization, a lot of scope for distribution is there, right? Limitations, obviously, as we go along, we might increase good number of hidden layers and everything, but eventually little bit of large data sets, it can be little slow. So but this can computational cost is high, but using the high architectures or high-end architectures, we were able to improve upon the performance for sure, but the computational cost would definitely go up. It might result in the problems, very typical kind of problems called overfitting and all those things. Data sensitivity also, because normal data needs to be normalized, right? So I mean, so these kind of limitations would always be there. And so, and MLPs are nothing but whatever you hear about deep learning networks are nothing but MLPs. So these are the foundational blocks for deep learning networks, right? So we'll now come back to the same problem, XOR problem, and we would solve this using a multi-layer perceptron. So you would get a taste of first MLP, right? So obviously, before we can actually look into this particular problem, so I need that how the XOR gate is built. Everyone knows about it. When both the inputs are same, then we get 0. Otherwise, whenever the inputs are different, we get a high value, right? Okay. So I need to represent this data first, visually first, that how would I represent this data? Because by seeing the distribution of the data, I mean, I am not able to separate it. I need a two separated lines, right? So wherever you see a scenario like this, where you cannot separate your data, you need two separated lines. That is where actually you can start assuming that you need a introduction of hidden layers. Okay, so this is also one of the ways in which you can understand that why should I need a hidden layer or not, right? So so this is a typical, I would say, representation of MLP that we would be using to solve the XOR problem. So here, these are the input layers I told you. So this would have the values as it is, right? I mean, this would receive the values, all these four values one by one, right? So we have introduced a hidden layer one, so maybe N1 or call it N2 or H1, H2, whatever. And these are typical weights. We will see how this can we can use different weights also, but these are typical weights on the basis of which we would be solving this particular problem. And then we have a output layer. So the hidden layer one, this hidden layer one. So this is a typical formula that would be working behind the scenes. So the hidden layer N1 is this one, right? N1. This entire portion is suppose N1 and this portion is suppose N2, right? Now this N1 is typically the OR function of this is typically would be given the role of a OR function of x1, x2. Yeah, you understand this? This is an OR functionality, right? And the second hidden neuron would be given a functionality of AND, that is AND of x1, x2. But it would also result in something called NOT of AND. So ultimately, this entire network is nothing but the NAND, right? This would be the NAND part, right? You will see that why this combination would work, right, later on. And this is the first hidden layer is basically doing the functionality of OR part, right? So OR and combination of NAND, and then OR and NAND, we would do the AND part. So AND of OR and NAND would be the output layer, right? And with this combination of weights that we have given, we would be able to solve this particular problem. How? That I will show you, right? So this is a typical calculations. I've shown that calculations later on also. I'll show you that how this works. So everyone knows about what is the output of or everyone knows about what is the output of NAND, and everyone knows about the output of AND, right? So start assuming this function right now, right? That is the first part. So obviously when you'll give both inputs 0 0, right? And this is typically what OR function, right? So 0 0 means it would result in what? 0. So you see it has for this it has resulted 0. So when it would give 0 and 1, it would result in 1, right? When 1 0 would be given, it would result in 1. And when 1 1 would be given, it would result in 1, right? No issues on that. Now coming back to this, this had the task of what? NAND, right? So first we would perform AND and then not of AND. So when I'll give 0 0, so AND would always produce what? 0. And since this is NAND, so it would result in 1. I hope no issues in understanding. Similarly, when the input is 1 0, output would be what? 0, because AND of 1 0 would be 0. But since this is NAND, so it would be not of 0. Similarly, for 1 0 1, when it is 1 1, the output of AND would be 1, but now it would result in something called, because it is not of this, so it would result in 0, right? Any issues in this understanding right now? All are on the same page?
Can you explain this part again, N2 part?
Okay, so understand what exactly we meant by this. N2, what functionality we put? N2, this was NAND.
NAND.
NAND. You understand NAND? You
Yes.
understand AND also. So we'll perform AND. So when you give 0 0, what is the AND value of 0
Zero.
0?
Zero.
0. But NAND would be opposite of
One.
0. That is
Correct.
1. Similarly, what is the output of 1 0 in AND?
Zero.
It is 0. And
Yeah.
0 का opposite क्या होगा? 1.
One. Okay.
Right?
Okay.
Right. Now, now we have to perform what? N3 is what? N3 is not of, sorry, AND of both these parts. That is N1, N2. Not, sorry, AND. So this is basically AND function, right? So AND of एंड ऑफ व्हाट? एंड ऑफ n1 n2. सो 0 0 0 1 एंड का कितना होगा? 0 होगा. 0 एंड 1 का एंड कितना होता है? 0. 1 एंड 1 का एंड क्या होगा? 1 होगा. 1 एंड 1 का एंड कितना होगा? 1 होगा. एंड 1 एंड 0 का एंड कितना होगा? 0 होगा. You got this? Am I clear with that, on this particular function?
Yes, sir.
So what it is giving? It is giving me the desired XOR function, isn't it? When both the inputs were same, I got 0. In rest of the cases, I got 1. Right? Am I clear about this? Yeah.
Sir,
So,
couple of questions, sir. Sorry for interrupting.
yeah. Mm.
So, sir, so the N1 and N2 represent the neurons, correct, sir?
Obviously,
And when we say about H1 and H2, I'm sorry, I'm
this same
uh,
thing, same thing, same thing. You can name it H1, H2 or N1, N2. It's same thing.
so I mean, just for understanding, like when we say H1, N1 and N2 is part of the H1 layer, right? Hidden one layer.
Yeah. So this is one hidden layer, one hidden layer, one
Okay.
hidden layer. Yeah.
Thank
If
you,
we
sir.
would have inserted in similar kind of case, so I could have, if I would have inserted two more hidden layers into it, so there would be another layer, right? If required.
Yeah.
So now I've just given you the working part, right? How actually it was solved. So obviously I would have solved this problem for H1 first. H1 means N1 over here, and H2 means N2, whatever you see, right? So H1 or N1 or function, H2 or N2 was the NAND function. So obviously I need weights, right? As I told you, I need a bias value, right? Isn't it? I would need certain values. And similarly, so these are some initialization values. I would need a learning rate. Actually, learning rates would never be one. It would be some real values, right? So by solving these initial thought process that we took, right? And you can see how the weights have been different, right? Weights for this is different, weights for this is different, you see. So when you would apply this, so this is the complete table which I've explained you in the before session also, previous session. I hope everyone is now aware about the different components. They would not get confused by this. So this
Thank
was
you.
your
I'm
initial
sorry, sir.
learning. Yeah.
I'm sorry for interrupting again. So I'm asking this because the notations what we mentioned for neuron and the notation that we mentioned for hidden layer, that's a bit confusing. Like because we're interchangeably using H1 and N1 together,
So do
representing
not get
neurons.
confused. So H1 or N1 is same thing, right? This is
Okay,
hidden layer. I'm only talking about hidden layer, right? You call
okay,
it H1 or N1, whatever.
okay, sir. My question is
So,
like, sorry.
uh,
So
yeah,
within a
please,
hidden
please.
layer, within a hidden layer H1, we are having multiple neurons N1, N2. Can I say like that? So
So in hidden layer one, we have two neurons over
yeah,
here.
so yeah, so each neuron has its own activation function, correct, sir? So here we are
Yes.
using N is having an OR
Hmm.
operation and N2 is having an AND
Yes.
operation. So within a hidden layer,
Yes.
we can have multiple activation function, and that is specific to a particular
Yes.
neuron. Correct, sir? Is my understanding
Obviously.
correct?
Obviously. Yes.
Okay,
Yes.
thank you.
Obviously.
Thank you,
Yeah.
sir. Thank you.
So, if you were present in the previous session, you would have been able to understand that we use similar kind of table, which contains everything. So these are hidden layers, then the output of the hidden layer, then we applied the activation, then error was calculated, then the del part, right? The error, then the weight, the change in the weight part, we calculated over here, the change in the weight, this bias part, and these are the weights that we got updated, right? So anyway, so as you can see, what I've done is, um, you would see, like, if you remember what I told you, that for all the epochs, we need a stage where what? What did I told you? That our target should be equal to what? Our target should be equal to what? Our
Output.
output part, right? So if you can see in this stage, yes. 0, and this is target part is. So, I mean, you would need, although I could not show multiple iterations over here, you know, so there would need multiple. What I'm trying to show is that you cannot solve a problem in just two iterations, three iterations, or four iterations. So these iterations would go on till a stage where, for example, I could not cover the rest of the portion where all these, so suppose this is iteration epoch fifth, right? So I need a case where this would be right. All the values should have been same. So it is still not the end of it, because if this is 0, then I should have retained 0 here. If this is 1, I should have 1 over here. If this is 1, I should have 1, and this is 0, 0. So I need a case where all my all my target values are exactly same as the output part, or in a way the otherwise you could have seen a stage where this 0 0 and all the errors would have been 0 0. I could not receive this in these number of iterations, so I would have executed furthermore. I hope we understood this in the previous session also. So why I'm talking about multiple iterations or multiple epochs, right? So this will go along, but it would be able to solve this particular problem. We tried to understood through these weight vectors, right? But since when it comes to network, the real networks, because real networks would not take these values automatically. Right now, what we did is we somehow assume these values, a perfect set of values, so that it worked for us. But when we would draw a network, so we would start with random values. You are getting my point? Because here what we did is we just took certain values which we knew how to work, right? And then we started. But in real network, I would start with certain random weights, learning rate. So it would take multiple iterations depending on what weights and what iteration, I mean, what learning rate and the weight functions, or what kind of activation functions you have initialized. So it might take, for one person it might take 100 iterations, another person he might do the same job in 10 iterations. So the real network would look like this, right? You got this understanding why I'm trying to make a differentiation of what I showed you in a very simple step through this particular thing, and real networks might take number of calculations. Okay,
Well,
is
I
that
have a
clear?
question.
Yeah,
Yeah, I'm
yeah.
clear with this. Clear with this, sir. But I mean, how we determine the activation functions, and like before we train the model, do we have to know about like every neuron what
Absolutely.
asking
So
us?
it is just
Okay.
like, yeah, it is just like, suppose if you're an architect of an building, right? So you need to have the basic understanding and basic thought process on where to apply which tool. Similarly, if you work in industry and on a machinery, so the basic understanding of the mathematical statistical understanding, that what kind of statistically how this function, I mean, this input is present in this form, what kind of mathematical derivation or mathematical treatment would be required. So those understandings should be clear, obviously,
Okay.
right? You can
So
just took, yeah.
sorry, sir. So it's not taken care by the model automatically. Like we have
No,
to
no, no,
define
no.
the
How? No, no,
function
no, no,
define.
no,
Okay.
no, no,
Okay.
no. So otherwise, it would have become a god. Otherwise, no, still it's not
Yeah.
god.
Yeah.
No, if everything would have been solved, right? So basic understanding of statistical understanding and what functions, activation functions, parameters. I mean, I told you like how you randomize your weights that might, I mean, take your job or make your job very miserable. One person
Yes.
might take thousands and thousands of iterations, and another person who might take these weights very smartly, no, he can get this done, work done in 10 iterations, right? So that's,
Yeah.
those things would obviously be there, right?
Thank you, sir. Yeah.
So MLP, just to give an idea, I would not take too much about it. So what kind of problems it solves? I gave you very clear thought process that today's deep learning networks are nothing but MLPs are the foundational blocks, because the architecture remains same. Because it started talking about multiple hidden layers and all those things, right? So, so I mean, when the MLPs were used very heavily before these deep learning networks, so they were they were the actual tools of the methods where we're solving disease predictions, all the typical kind of problems that we still solve. And if we're using simple MLP, so they would be able to solve all the problems that we know, right? So I'm not going into this, right? So practical uses for MLP. So wherever you can see the uses of deep learning networks, it is same the uses of MLP, right? And everyone knows that what kind of problems it solves these days today. So the idea is they're able to handle both structured and the unstructured data as well. That's the beauty about these MLPs, right? So what I'll do now will I just wanted to cover certain aspects which was not in the part of the presentation, but I really feel that you should have a little bit of an idea about different activation functions before we actually start jumping to linear, how to use new MLPs to solve linear functions, right? So before that session, we'll do a quick, we would not take too much of time on this, but understanding of various activation functions would help us in our eventual understanding of rest of the things. So why activation functions and why we use them is an important thing. By now we got the idea what exactly activation functions are. So I told you that when the input, when the summed input, yeah, as you know that what we have done is when this is taking what summed input, H1 is what I1 into W1 plus of this I2 into W2 plus of B1, that kind of input it receives. Yeah, everyone aware of it is. So, so when it receives this summed input, so when it so I mean every init or every neuron when it receives certain input, so it has to take a decision. What kind of decision? Whether I should activate or not, I would fire or not. I mean whether I should pass my input to the next state or the next line which is attached to me. For example, H1 is attached to the W5. So whether I would inhibit this whatever I have received or whether I would pass on whatever I've got, right? How would I pass upon what I got is also needs to be understood. It's not that whatever I would receive the same way or that much amount I would pass on to the next layer or next stage, right? So that decision, so first whether the neuron would activate or not, activate means whether I would pass it or not, that decision has to be taken. Then how that signal should be passed. That's what I'm talking, right? Should I pass whatever I received, or should I consume little bit of or cut down something, may convert, transform it into something? So we started talking about transformation, right? Isn't it? For example, I would apply a simple sigmoid function. So sigmoid is a transformation. What I received would get transformed into another form. So transformation is the second part, right? The purpose of the activation function is to reduce non-linearity, right? If I'm going to pass everything, then non-linearity is not there. But if I'll do something with that input and would do some kind of transformation, then I can bring non-linearity into my output, right? Is that okay to understand that? Although we would be covering much about this thought process, that the idea now is that the activation function brings in what? Non-linearity into my data. Why we needed non-linearity? Anyone? Anyone who can answer this? Why I needed non-linearity now?
Because the
Because
data
Anyone who?
point were
Yeah,
not separable.
separable.
yes,
Absolutely. Because I would have separated otherwise, right? It would have been a
Yes.
simple case. So that's the reason activation functions are a kind of God particles, I
Okay,
would
so
say, right?
for the
Without that,
same reason we
yeah,
so for the same
yeah.
reason we cannot use the linear regression.
We can use linear regression for very simple problems. I'll show you in the that was the next session only. I'll show you that, right? We can use linear regressions by simple networks, right? Multiple perceptrons, but not all kind of. So obviously linear regression, wherever the data is separable, I can use it as a linear regression. Where the data is
Hmm.
not separable, I have to use it for complex network. That's the only case, right?
Okay,
Sir,
okay, got it.
say,
Yeah.
sir, sorry to interrupt, sir, but that was our goal, right? We wanted to make things linear, put it in different planes so we can analyze.
So
But
that is
now,
what I'm. Yeah, that is what I'm saying. So I didn't told that we would convert this neural network into some other kind of network. We would convert this neural network into multiple hidden layers, right?
Yeah.
So
But then
idea
for
is
the
what? Yeah,
activation functions to introduce non-linearity into
yeah,
the output, right? So
I
that's
got your
what I'm
point.
trying to understand. Yeah,
Yeah,
sure, sir.
that's what. Yeah, very good question actually. So what he's trying to say, or what he's trying to implying is, eventually, at last, all my problems would get separated in a linear way only in higher dimensions. That's what you wanted to try to say,
Yes, sir.
right? Yeah. So understand that. So it is not that I would do some different thought process for linear functions and some different thought process. So the thought process would be introduction of the hidden layers only. So these hidden layers eventually would be bringing non-linearity, but eventually at last they would be separating my data through drawing a linear line into higher dimensions. Is that clear to understand this topic? I mean, this statement, we would cover on this statement in more details, right?
Sure, sir.
So
So it is just the transient state is what we can say, right?
absolutely,
Non-linear.
very true. Absolutely. It is just like, as I told you, my data was by naked eyes. I was not able to see my data separable. I took it into higher dimensions, and still I was not able to do it. Then I took it much higher dimensions. In the higher dimensions, my eyes, naked eyes, was able to see that yes, now the blue lines or blue dots are separated and the green dots are separated. I can draw a line. So ultimately, in higher and higher dimensions, I'm doing it by separating the line. But right, but in a lower space, I was not able to separate my data. That's the only
Sure.
point.
Thank you, sir.
So why do I need activation functions? Because without activation functions, the entire neural network behaves like a simple linear function equation, like even many layers together act like a. So obviously, if I would not use these activation functions, then it would be actually a single layer only. Work of single layer and the use of multiple layers would remain same actually, right? So so obviously they would not be able to learn complex patterns. They cannot solve simple problems. I think now the idea is very clear into your mind that what exactly activation functions are doing. So internally,
Sorry,
what? Yeah.
sorry, sir.
Hmm.
Sir, you said like a neuron might not pass on its output to another neuron. There were cases.
Yes. Yes, it
So,
would be.
okay, but
We would right now in any of the applications we have not used that thought process. There would we would come along when we start doing it, especially what happens. Um, I would, in fact, it would come, say, like when we are back propagating. It's not that every time you would use a case. So it is like some neurons have already learned something, for example. Understand that point. For example, you have thousands of students who are coordinating for a given task, for example. So in the process, it might happen then when you do multiple iterations, the some of the students as neurons have learned something, they are perfectly learned. So you would stop you would stop changing their connected weights of that particular student in a way, right? So that you would say
okay,
that this student has learned. So because if he would, in spite of learning, then he would start changing his weights. So he might bring into another aspect, right? He might forget what was learned. So
yeah,
that is the thought process, right? So I mean, I'll come to that thought process, right? Because that is an important question, and that is how everything would be based upon.
thank you, sir. Yes,
So what exactly is happening internally if someone asks you? So activation functions are nothing, but they are doing suppressing these weak signals, the thing that you was talking about. So in some case, they might suppress the weak signals, they might strengthen the important signals, and all is happening through weights. Everything is happening through weight values. So if they suppose some of the weight signals are weak, so I would tend to improve the weights. I would tend to increase the weights from negative to positive, or from lower values to higher values, right? Similarly, that is the case of strengthening. In some case, I might want to suppress some weak signals, right? I have to create feature transformation that I've already talked about. So help the neural network learn hierarchical patterns. So there are different kind of patterns that I would like to learn, right? Not only hierarchical, that can be other complex kind of scenarios or patterns that I would like to learn. So very typical and a very popular example what different layers can do. So for example, in image processing kind of task, so layer one might be responsible would be responsible, or in a way are finding or recognizing the edges. Layer 2 might do shaping. Layer 3 might actually be able to identify eyes and nose, and layer 4 might be actually then completing the actual work, that is completing the face. And the beauty about everything is that while doing everything, we do not know anything that how has it happened. It's not that I can dictate the network that layer 1 will do edge recognition, layer 2 will do edge shape recognition, and layer 3 will do eyes or nose. I do not have any control. The control is automatic. So what I'm trying to say, it might be a little confusing to you. Like I have in a way created the network, the values and all those would get into place, right? But how these layers and which layer would actually work on what it would extract, what kind of features, it is beyond my control, because it is the values which is taking place. All the calculations would happen automatically. So the only thing is that eventually I would understand, eventually the network would try to, only thing which is doing is that it is transforming your data into very higher dimensions and automatically solving it, right? So I cannot, I may write while teaching that layer 1 will be doing this, layer 2 would be doing this, layer 3 would be doing this, but actually I does not know what exactly goes behind the scenes and what kind of separations it would do, right? I'll talk about this particular thought process maybe a few slides after, because ma- you got my point,
Sorry
what
to
I'm trying
interrupt.
to say.
Sir,
Yeah,
one quick
Sir, but
question,
we
sir.
are
Sir, if
only
we don't
designing the,
control this,
yeah.
yeah.
so if we don't control this, how would we define weight and biases? Because I would
So
need to
that's what
know.
I do. That's what I'm trying to say is, it is just like very simple example. Um, you you control the, say suppose if you're teaching a student, for example, right? Make a child, you're making a child to learn, right? So you can control through these parameters what is the input and output, obviously, that is known to you. Yeah, please understand that perspective. So what you know is the input and output. That is what I have. This is the input, and these are the training examples I have, and this is the outcome or the output that I want to achieve. Yeah, I did control little bit on the process, initial process, and the output process through some kind of parameters, right? Now can and have started talking, and suppose 60 students are learning the same thing, right? And the same training examples. Now after say suppose 15 days or 20 days when the learning is over, can you tell me that which student, every student was able to answer it, but can I tell you, or can you tell me that how a student learned, and every student has the same learning? No, first of all. And then I can say that can you ask me, can a student can tell me that what is the step 1, what is the step 2, what is the step 3, that how a student learned? So that learning which is happening into your brain is very complex pattern, and you cannot explain it. You getting my point? You cannot
Yes.
explain that factor. You can only control the initial and the output parameters, all those things. But how a student learned, how that function got formulated, no one knows about it. And that is the beauty about these. When we're starting talking about neural networks and machine learning thought process or deep learning, right? So that is still a black box. You cannot step by step, you cannot make it draw it on the book that this is how I learned step 1, step 2. So in other words, you cannot define that algorithm. You know, that algorithm cannot be defined. Algorithm, you know from where to start, how to start each and every step, you know, right? And every step would be fixed, right? So why I told you, because if we knew it, if we knew that particular algorithm, then I would have taught every student with the same input and output and same learning parameters and same training pattern. Every student would have learned the same thing in the same amount of time, the same exact time, and the same way. That doesn't happen, right?
So,
So
sir,
that's
we
the
will
difference.
we'll architect and design neuron how it works and functions, but
Yes,
the sequence of
yes,
neuron is not in our control.
exactly. So So, and it is also the beauty about is that, so suppose the same so suppose you've developed a network, everything, right? And same input you gave, and you run one iteration or or the entire iteration, for example. Now, after some time, you again ran that particular network, the same inputs, but it might behave differently. So it is called non-determinism, non-deterministic behavior. That is also a possibility, right?
Sure, sir.
So
Thank
that
you,
is
sir. Thanks.
also a possibility. Yeah.
Okay.
So I mean,
But for example,
we,
can you hear me? Yeah. So for example, we have a XOR gate. Previously, we have
mhm.
discussed in previous
This
slide.
is very simple.
We
Yeah, if you're talking,
yeah.
if you're going to correlate my
No, I'm
thought,
not.
yeah, yeah, please.
No, what I'm saying is that in that we were using three neurons. One is OR gate,
Yeah,
AND gate, and NAND
yeah,
gate. Okay.
yeah, yes,
And then
yes,
we divide the weighted function and we define the solutions. So in this
yes.
case, everything is defined. So what exactly is not is missing? Like you mentioned that we don't know what exactly happens in the deep
So
neural
this
network, but we
is
are defining here everything.
yeah. So little bit of this was a very simple problem, my dear.
Hmm.
Very simple problem. It is a controllable brain, I would say, at this stage. You know, whatever I'm
Okay.
talking about is in a realistic condition. This is a very, very simple problem, right? Even if the iterations would happen multiple times or whatever number of time, it can be mapped back, right? And so,
Yeah.
so the same example, if I show you, right, for the same example, that's the reason I showed you
Hmm.
through this, right? On the other hand, I showed you through the values which we take an assumption. At this stage, we took an assumptions because we knew that because we already solved this problem. So I know that one one रखने से ऐसा होगा, one यहाँ पे रखने से ऐसा होगा. I knew
Hmm.
it, right?
Hmm.
Right.
Hmm.
But if I would have thrown this problem into real world, so it might have started working this manner, where the weights would have been randomly initialized. I would have taken, for someone would have taken these weights to be starting with suppose point 0.1, point 0.1, point 0.3, point 0.4, anything. No, anyone would have taken anything randomly. So so this would eventually started from the beauty is that it would eventually learn maybe in a smaller way or a number of iterations might increase or
Hmm.
a number of epochs might take. So that's the reason I showed this aspect also. So we were trying to figure out that what is the epoch where all the target and output was same. Still after 5 iterations, I was not able to achieve this, right? So
Hmm.
in other cases, a smart initialization of these weights says for example the weights that I took directly, right? So a person might have done some kind of research and would have taken these weights the initial step only, right? So he would have taken only 1 or 2 iterations then, right? So that is what I'm trying to say. So a lot of things in neural network is I would say randomized. A lot of
Hmm.
things is experimental, right? Where you learn and depends a lot of things depends on your initialization part. So a lot of research goes on this aspect also, right? So learning is you're controlling the learning, but how that learning is going, you know, behind the
Hmm.
scene, it is not under your control actually. No, completely. Yeah.
Okay.
So, you can go through these. What are the practical use cases of MLP? Yeah, these are all, I mean, you can correlate what is happening today. All these examples, disease prediction, EEG signal classifications. I've took very recent kind of examples only, drug response modeling. So whatever you can assume that what can happen through deep learning networks, everything can also be assumed through MLP. But obviously, deep learning networks involves many more advanced concepts and thought processes, right, these days. So, mm, so yeah, we were trying to do these activation functions, right? So this we did. So, I mean, so what is non-linear? So most of the I told you the real world representations may not be represented through a straight lines. There are many problems, right? Like face recognition, pixel relationships are highly complex. Speech recognition, sound patterns very dynamically, right? Symptoms interact non-linearly. So these are some of the examples where when you need a non-linearity. So just to give a little bit of understanding that how so this is so layer one would have been doing what, for example? assuming the same network that we built previously. So it would have been a similar kind of thing. And first layer 2 might be doing this kind of thing, right, and this is happening, you know it, right, what is doing it, so eventually y might be looking like this. So what I'm trying to make out from this entire thought process, whatever we did whatever we did over here by introducing the layer 1, layer 2, whatever, so what I received over here is this is still linear. Understand that point, right? It is still a linear function, right? So, so multiple linear layers collapse into a single linear layer. Can I say that? This is the output neuron. We introduced two neurons, for example, in layers, right? So ultimately, so the same thought process that we were trying to show, it was only the representations were transformed, but ultimately the work would be done in a linear fashion only at the last stage, right? Similarly, another aspect is what? Linear models cannot create complex decision boundaries, right? So linear models can create these things, okay, but many data sets might require curves, closed regions, it might require multiple separate regions, irregular boundaries, right? For example, uh, I think, yeah, just wait. So, I mean, what we're trying to say is that what is the need of non-linearities? So I explained in these three steps. Now what we'll do is I'll cover certain activation functions which are very common. It should not take any time now. This is one of the very basic activation function. We call it as a step function. We can call it as a binary threshold function, right? So it is what? It would result in X. I think now you can understand. This can be the summed the weighted connection that I would receive, as a function. So activation function might result in 1 or 0 value. So this could, and this we called as what? If you remember, this value is what? Threshold value, if you remember, isn't it? I talked about this was the threshold value, if you remember, right? So
Yeah.
so if it is greater than equal to 0, so it is now again, it is the control of the programmer over here. So he might say that no, only greater than 0, and here he would have written like this, right? So that controls a lot of aspects actually. So the programmer has to, it is just like a person who is architecting a house. So he has a lot of control, right? But ultimately it would be built by the people who are the laborers, right? So so purpose is obviously mimic the biological neuron firing, produce the binary output, use in very early perceptrons, not much work. You can do a very simple binary classification task, not differentiable. I'll talk about this. You might get confused, right? That this function is not differentiable. So a question directly comes in, why we need differentiable function. So I'll give the answer, right? Just wait for some time, right? So you got my point. Why we need it is not differentiable. I started a question and I'm telling you to wait, that this function is not differentiable. So the question comes in, why you mean by differentiable? Why there's a need for differentiable function? For that, I have to explain little more concepts, and when so we would return to this particular question. So this function is not differentiable, and why I need differentiable function, I'll talk about it later. Zero gradients. Again, I'll talk about this. It cannot train deep networks, obviously, right? So it is able to do a simple binary classification kind of task, and they're two very simple, right? Another activation function, I'll focus now only on the different type of activation functions so that I can come and jump to what I was trying to say. So this is a very simple activation function. What it does, whatever it gets, it passes the same thing, right? Well, yeah, we call it as a linear activation function. Whatever it gets, it would pass on exactly the same thing, right? So this would be a linear value. It would pass the linear equation, whatever it receives, right? So obviously graph is quite visible. So passes input the directly, no transformation, and the range can be, obviously the output range can be -2 plus infinity over here. So it is would definitely be very useful in regression. Yeah, you can all understand this. We would be using this for predicting the continuous values, for example, temperature, stock, and age, whatever. There can be number of cases. So no non-linearity and deep network collapses into linear model, obviously. So ultimately, I mean, it means that it can only solve the linear kind of functions, right? Another was the sigmoid activation function, right? Everyone knows about this formula. The purpose was it would convert the values into probabilities. There are many networks that uses this kind of thought process where they converts the outputs into probabilities, and based on the probabilities they need to take some decisions. Like for example, logistic regression you might hear. Smooth activation. We are just covering the activation function right now, so do not get bugged up that where and how we would use it. The output range is 0 and 1, so all the values would it would throw by converting from this activation function would be in the range of 0 and 1. So it is a very ideal case, and most of the cases we want to throw that function into the range of 0 and 1, which very nicely gets intermingled through the probabilities prospects, right? So they're smooth and differentiable. I'm still holding this question back. Why I need a differentiable functions? Their probabilistic interpretations are very possibility is there to link it with the probabilistic interpretation. So they are again very useful in binary classification, logistic regression, as I told you, probability estimation, and there are many examples that we solve it, which requires a binary classification like SMAM detection, disease prediction, many things. Still, I mean, this particular activation function suffers from some of the basic issues. And these issues, as you can see, I have written in front of you, is something called vanishing gradient problem. Again, when I would explain what exactly gradient problem is, gradient descent problem is, then I would explain. So, very simple term, vanishing gradient problem means that the network eventually, after some time, stops updating its weights, or that would lead to non learning, right? So weights become very very small and they stop learning. So that is a vanishing gradient problem. I'll come to that. Saturation at extremes, this is another problem. And slow learning in deep networks, right? So what I'll do is, let me explain these vanishing gradient problem, because it is required and everyone must understand what exactly it means. So, um, although at this point of stage you might get little confused because we haven't talked about gradient descent, but I'm trying to bring in this concept because uh, this might give you a little bit of clarity. So, in case you do not understand it, so please hold back your thought processes. So, so what I'm trying to say is that when you do training in new network, like for example in higher networks like multi-layer perceptrons, so you use gradients, you use derivatives, you would use back propagations. So what exactly gradient does or tells you that how much weight changes. I think I should not use this at this point of time. You might get confused because I didn't tell you anything about gradient descent. So let's skip this, right? So vanishing gradient problem, just remember that uh, uh, when multiple iterations would happen, when the back propagation would happen, so the networks stops receiving any change, right, during the back propagation, and that is where the network stops learning. So excuse me on this slide. I should not have inserted this slide in this point of time because I have not talked or opened the learning about something called gradient descent, right? So we'll talk about this later on. So this is just an example. You see, sigmoid function. So when I would do a derivative of it, so I mean, so the values might always in this particular region. But since I'm going to multiply each and every, so if I'm using 10 layers, if I want to multiply it with these kind of values, so these would become very small. So gradients become very very small. So gradients almost become zero. So this is the kind of thought process which you might not understand at this stage. Excuse me on this slide, right? Uh, yeah, this could be a very simple thought process that you can understand. I should have inserted this. So suppose imagine that passing a message to many people who are standing in a queue, for example, right? So every person whispers message very small, softly. So eventually the message would disappear when it goes to suppose 10th person in that particular queue. So that is called a vanishing gradient, right? So this is the same thing happens in neural network. So input to layer one to this and this. So when you start, uh, so when the output layer starts giving the error back, so so layer 4 will get some percentage of error. Then that layer 3 might lose some kind of error and would receive some percentage of the error. Layer 2 might receive some percentage of layer 3 error, and eventually this layer might receive no error at all. So when it would receive no error, it would stop learning. So that is the kind of thought process that we understand through gradient, right? We'll come to that later on, don't worry. So uh, saturation at extremes, this is also one of the thought process that I presented when I talked about this sigmoid function. So sigmoid what does what? It skews your values between 0 and 1. That is very simple, right? So for large, very positive numbers, this would return 1. And for even very large negative numbers, it would return this, after applying the sigmoid function. So these regions are actually called saturated regions because the output would change very little, right? So for example, over here, you can see that I've given X. When I applied the activation function, it is 1. Even if I say 101, it would still result in 1. So saturation has achieved, right? So, so I mean, derivation becomes 0 or the same value in the saturation regions. And this is what results in something called gradient vanishing problem, because when the changes I would not be able to identify between the changes, the learning would stop. So saturation is dangerous because the neuron saturates, it becomes insensitive, the output barely changes. So anything that where the output starts becoming fixed nature or does not change, or the weights does not start changing, so the things becomes inactive, right? I can understand that these slides may confuse you a little bit because the ideally the activation, I mean the gradient descent problem should come first, which would come little later, right? And that is where, because loss function needs to be explained very nicely before covering these aspects, right? So I just wanted to talk about these activation functions because when we would start talking about networks, I would start using these activation functions, and you might be in dilemma that why this and why not this, right? So there's another kind of activation function that we call is a tangent hyperbolic functions, right? And every activation function has some advantages and some disadvantages, right? So therefore, if it has some of advantages, so it might be suited for some kind of activation function, some kind of problems. Another activation function might be suited for another kind of problems. So so here, as you can see that tangent, so mathematically it shifted versions of the sigmoid functions. Both are similar and can be derived in each manner. So you can see that the range, so it range does matter. So in the previous activation function, the range was between 0 and 1. But at times I need, why can anyone give me a thought process like the in the previous example, my range was between 0 and 1. Why? And give me a scenario why I would like to have a bigger range in where the my activation function can behave. Anyone? Why I would need a bigger range where the
So
output can be
when
thrown?
output is not binary, you need more types of output.
Yeah, little bit more on this. We talked about in a different manner in our today's talk.
Maybe positive and negative errors.
More on it. Yeah, more. We talked about it. Anything which we talked about, that introduction of hidden layers, anything to relate with that? Why I'm introducing hidden layers? Why I'm introducing hidden
To
layers?
bring to introduce some
Introduce
non-linearity.
non-linear.
Non-linearity. So when I introduce non-linearity, I need a smaller space or a bigger space. You need a bigger space
Bigger
of
space.
numbers. Yes, and a very
Yes.
logical interpretation. You got my point. So my
Okay, sir.
range would be small. So I would not be playing area would be very small for me, 0, 1. You know, and -1 to 1 would be a bigger playing region. I would be able to explore the multidimensionality of space in a bigger manner. And that was my thought, isn't it? So
Is it something has to do with weight decrease like negative weights we have? It's not
also
related,
about
correct?
this, no, it is
Okay.
related. That is, it's
Okay.
almost, see, if I'm going to only allow my weights to be positive range only. So I've given a
Hmm.
small region, a small
Hmm.
search space, I can say. Now
Hmm.
I've increased my search space to bigger region. You can
Hmm.
take the weights from -1 to 1 region. So that's the reason, yeah,
Okay.
isn't it? And then I also told that some of the neurons would stop learning. You know, some of the students, I mean, some of the students or the neurons who were not learning. So I would be able to represent quite well those who are not learning, so still negative, right? So I can make it towards positive kind of thing. So I would be able to correlate many of the things, right? So that's the thought process. So, but this function, tangent hyperbolic function, is still, it suffers from vanishing gradient problem, the same problem that we saw in the earlier activation functions. So, how do we deal these gradient? So, this is, you might see eventually when you would learn that vanishing gradient problem is a very huge bottleneck, a very huge problem, right? Even the best of networks, that can be it can create a lot of problems, right? So so eventually this relu, it was like a very very effective solutions that actually was able to handle. So what I did is I opened my network space, I opened my the range, I mean the search space, by bringing in -1 to 1 or even a bigger range, for example, right? Now because of this, what has happened is that the vanishing gradient problem is still there, because when I will introduce -1 and 1, all those weights, so the minus effect when multiplied, you know, it can result in a not only zero, but it can reduce it into negative direction also. So the learning might become negative at some point of stage. So it can result, I mean, the learning can be drastically affected. So in order to handle this, so they brought in the experts or those, I mean, some person who would have, you can do the GPT, that who actually discovered this ReLU activation function. So, so what it does, it brings in a very simple solution. The function works like this, right? So either it would, so if it is max of 0 comma x, so if it is positive, it would result in x, obviously. And if there would have been a negative value, right? So if it is less than 0, it would result in 0, right? If it is greater than x is 0, it would result in x. So very simple function mathematically, but it worked quite wonders and was able to handle something called the vanishing gradient problem, right? Because what it does, it was able to suppress the negative signals, right? It was able to suppress the negative signals, but we did gave the search space a bigger one in the form of -1 to 1, for example, right? That was required. I wanted to play around in a bigger playground area, right? So limitation is that it should only be used within the hidden layers. So whenever you would see in the biggest of networks also, so whenever we see the hidden layers would always be marked by the ReLU activation functions, right? Okay. And the output layer, for the output layer, we do not use ReLU. We normally use softmax functions, which I'll explain in the next slide, right? So always remember that whenever you would see hidden layers, you would be using the ReLU activation function most of the time, because they are mathematically able to handle the vanishing gradient problem. We would talk about this gradient descent algorithm maybe
Sir, quick question on this one.
Yeah.
Sir, how will it handle vanishing gradient problem, right? If it's some value is more than one, right, it would still limit it to one, right? So on that
No, it
side,
is
so
talking about negative, on the negative part. Dekho. If it is less than x is less than 0, for example,
yes, sir.
so it would result what? 0?
Zero, zero. Yeah,
Yeah.
it's yeah.
So what it handled is, and because of those negative weights, it was making my learning, it was stretching my learning continuously towards 0 or towards negative side, right? In a way, it would suppress some of the neurons in a way, or it would handle some of the neurons by suppressing its output, which it was giving as negative. So that is how it would be able to handle it, right? What I'll
Okay.
do is in the next session, what I'll do if I'll get us, I'll give you a working example also, a numerical example that would make this thought process very clear, right? It would be very clarity that how this ReLU, I mean this if the outputs are negative, then how it is affecting it, है ना?
Okay, sir. Sure,
Or
sir.
in fact, my previous slide does talk about this, but I doesn't want to confuse you. This particular slide does talk about this, but since I have not talked about these derivative and all those, so I doesn't want to make you confused, right? Anyway, so ReLU, there are different, I would say, methods or different kind of ReLUs. We may not talk about this later stage, at this particular stage. So, I mean, just for information, there's a ReLU, there's a leaky ReLU, there's a randomized leaky ReLU, right? So because merely using ReLU function may also not work. Another problem with ReLU is that some gradients can be fragile during training and can die. So it can cause a weight update, which makes it never activate any data point again. So, I mean, that's what I was talking about. Because if you keep on making some of the neurons 0, 0, 0, because it would, so it in eventually in a matter of time, it may happen that many neurons might become 0. Can you visualize that? Because it is wherever the neuron which is throwing out output as a negative value, it would be actually resulting in a 0 value. And if many neurons start doing that in a network, then these neurons would become a dead neuron. You getting my point? So, to fix that particular problem, what they introduce is called a leaky ReLU. That is, it would not result 0. It is just like a voltage. Voltage cannot be 0 and 1, right? So what that does is it would result in some value, but it would never result in a 0 value. So this factor would come into play, right? Let's not talk about this because activation function was not an thought process in this particular lecture. I just introduced it because when I would start talking about some of the networks, so I wanted little bit of clarity that why I'm using this, why I'm not using it. Did anyone got this thought process of leaky ReLU? Because little important, because some of the neurons would become 0, you know, they would start producing every time 0, 0, 0, 0. So we doesn't want that, right? We wanted to convert, we wanted to keep it a positive. So it would be AI into XI. AI would be a small constant, right? So, but not 0. So this would result or solve the problem of dying neurons. It introduces a small slope to keep the updates alive, right?
So it's like a bias, sir, right? We introduce
Kind
a
of
small
bias.
bias.
You
Yeah.
do not call it a bias because bias has a different purpose, yeah. But
Sure.
yeah, yeah.
Sir,
So
so I
yeah,
had a question.
yeah.
Yeah. So let's say, for example, we designed a network, and
Hmm.
like there are hidden layers. But let's say, for example, it's a general question, sir. So
Hmm.
let's say, for example, my output, like there is a lot of error, and
Hmm.
I'm not getting to the output that I really want. Okay. So
Hmm.
how do we deal in this case? Like, do we kind of debug?
Hmm.
How do we debug?
No, no, no. So
Yeah.
you have to little wait till I would start explaining about the back propagation neural network, right? That is where you would understand that how that error gets propagated. We use something called chain rule. You know, it is a complex method, but you have to wait till that point, right? How
Okay.
that error gets propagated. It's a complex function. We call it as a chain rule, right? And you would get that understanding very clear. You have to wait,
Okay, sir.
right?
Okay.
Yeah. So there's a lecture devoted to that on back propagation neural network, right? So, I mean, you can, I mean, this would keep it a little bit of understanding. So it decides should the neuron would active or not. I think I've explained it, so not a very, um, just to give an idea that how activation or ReLU function is being used, right? So if you have these kind of X1, X2, you know, and so you see this particular small thing, but it is important. So this x1, x2 is still 1 when I use RHS. So did you did you get this thought process? So we are able to see that x1, x2, LHS. So in spite when I apply a function, still it is LHS is not equal to RHS. So what it would do is what how does a ReLU can take into this? So it actually creates a kind of a kink, right? A band at x is equal to 0, where it can take a decision. Otherwise, how would a function would take a decision in this particular case? Because even when this is the case, LHS is not equal to RHS in both the cases where, I mean, this is, I hope everyone knows. So if it is a function is a linear, so this is a property for linearity. You know this? Everyone is aware about a little bit of mathematics, right? So that is it becomes so that is how I mean non-linearity would come into play. Anyway, let's forget about this. We would not, I doesn't want to confuse you more. Softmax function is another important function where in most of the networks, the output layer, you would find softmax function. Why? Let us understand a little bit of more. So suppose that you are at a quiz show and you're not sure about the answer. So instead, what you would start picking one answer from the full confidence. Say you might say that I think A, 70% are sure about it. B, 20%, possibly C, 10%. So what exactly the same thought process is done by the softmax functions. In this process, also assume that what exactly is required at the output. At the output, I need a classification or I need most of the time I need a classification task or a regression task, isn't it? That is what I need at a output function. So so softmax lives at the output layer of the classification network, whereas wherever the model must choose between multiple classes. So obviously in the output layer, I might have multiple classes. Layer, I mean class 1, 2, 3, 4. So how would I understand that class 1 means what? How would I understand the class 2 means what? Class 3 means what? So because everything in the form of a numbers, whatever I'm getting calculations and whatever my network is doing is always in terms of numbers. So so I need something where the softmax function how it is able to solve. So, so for example, I may have this cat, dog, bird. So three categories are there at my output function, right? Or maybe suppose ma'am, no promotion box, whatever. There are different kind of output classes might happen. So what it does, do not get confused, right, by looking at the formula. So this is how we call it as a logit. The scores or the raw scores, we call it as a logit. If someone has done logistic regression, they might be a little bit aware of this, right? So the softmax function does what? It would convert each of its scores, that is the raw scores or raw values, into probability, right? By using this thought process, a simple thought process, right? Breaking it down. So this term, it makes all your scores positive. Obviously, exponential is always positive. Everyone knows it. And this term will take the all the sum of the exponented जो भी scores हैं सारे के सारे को उसने add up कर लिया है ना. It has summed all the exponential scores that it has calculated, right? And then dividing is why? Because each score becomes a fractional of the total probability. So this thought process, actually, if you see, I've given you a working example also because at times mathematics is not able to explain little bit of things. So suppose this is the case, right? You got a raw score like this because what you achieve, network doesn't understand these. Now, what network would always get these values kind of things. So I can take these scores, right? For example, it receives this depending upon what values have thrown, right? You took a sum of all these, right? And then what you did is you got the probability of C, P. Now you can start assuming the thought process that I want to classify cat, dog, or bird in this fashion. What is the probability of cat? So I can define a range out of it. I can define a range for this. I can define a range for suppose a bird. So if the probabilities fall into that particular range, I would define it as a cat. If the probability is defined in the range of this, I can define it as a dog. So that is where I can convert that particular set of numbers or thought processes into a classification kind of thought processes. Are you able to get a little bit of it? So, or in other words, I could convert this into kind of probability. So highest probability got what? 82, because this is, so I would classify it as a cat. Another way of doing it, right? So mostly we do it like this way only. The highest probability. So out of this is a cat. है ना? Did you get this? What I'm trying to make? I just want to trying to insert little bit of thought process before we can start thinking of, or otherwise I would start saying that I have used softness function, I have used sigmoid function, but you would not have any kind of clarity. So softness functions would be used at the output layers. Everyone got this thought process little bit? If not in an entire manner, but little bit of idea. Got this? Can you hear me?
Sir, what if two scores are close?
So two scores are close. Obviously, I mean, it would throw some of one of the values a random value or something, right? No, or otherwise, something needs to be done, you know, because it would pick up one of the values. So some kind of algorithm would have used in first come first or whatever it picks up in the first case, because it would not throw both of the cases as an outcome. It would pick up one and throw you. So. mm, So in a way, raw scores can be negative, properties can't. No. And it amplifies the differences. The high score gets the differential boosted, right? So it's not that the softmax function is limited in this fashion only. So there are a lot of other ways in which this softmax function is being used. I just wanted to give a little bit of thought process. Yeah, I wanted to explain this thought process also, right? Because although I have not explained the gradient descent, why do we need differentiable functions and neural networks? So differential functions are required because neural networks learn using what? Understand that at this stage, that by what gradient descent is just like that, how those errors, right, from the output layer would get propagated so that the weights would get changed. You know? So how this would be done? This would be done by a gradient descent algorithm, right? Understand this understanding about gradient descent, right? And how that eventually or with iterations, this error would keep on improving or keep on decreasing rather, right? But rest, because when we would do gradient descent, I would explain that. So these learning algorithms would depend on what? The derivatives. These derivatives are gradients. So for example, the total error is suppose E at the output layer Y, suppose, right? At the output layer, suppose the total error is E. Now I would like to see the contribution, the total error del of E with respect to weights, right? So what is the total error, how the total error would change with respect to the change in weights. So there might be weight W1, there might be weight suppose W2. So how the W1 would respond to the change. So how the error would respond when W1 would change, how the error would respond when the W1. So small change in W would respond to error change, right? So gradient cannot. So what happens if these functions, whatever we're talking about, they would not be differentiable. So we would not be actually able to compute these gradients properly. So weights cannot update efficiently. So in a way, as of this point of time, the functions would be differentiable. Otherwise, see, understand, for example, there are two person. Let me give it a more simple way. So in a group of, in a companies, for example, you have given some task, right? And the and you have to, and say, suppose a set of four people, just wait. Sorry. Suppose a set of four people solved a problem, and they gave some kind of outcome, right? Now you want to see that how, based on whatever they did, you want to give them another set of tasks. Obviously the same task would not be given, and considering that you have to do a particular big task. So how, as a manager, depending upon you have seen their functionalities and your their abilities, I would say a kind of error what they make. So you would give some proportion of the total task, we call it as an error, whatever, to W1, some proportion to W2, some proportion to W3, if we consider them as different individuals. So how the error would get propagated, what is the total propagation of the error with respect to W1, with respect to W2, that is the thought process. And unless I would be getting that kind of ability to do so, and this kind of ability only gets through when I had the opportunity to have derivatives. So that is what I can explain at this point of stage. So weights cannot be updated efficiently unless I'll get, or unless my functions are derivable, right? Because I want because error cannot be distributed equally to all the weights. If suppose there are thousands of weights which are connected in the network, so error, all the thousand of weights cannot equally handle the error, or would equally handle the error in the same way. That's the thought process, right? So the neural network learns that it adjusts the weight slightly to reduce the error, and every neuron or the weight would adjust the weights differently. Differently matlab they would contribute in a different manner, right? So which direction to move first of all, and how much to move. So that is what the derivative comes into play. Now, so I mean, see, I would like to move in a direction, or how much to move in a way so that my error becomes minimum. So that these two aspects is decided by something called gradient descent, which is a derivable function, right? So we calculate this, the del of error with respect to the weight. So this derivative actually would tell you, so you can understand these 2 points, that how sensitive the error is to the weight, and whether increasing or decreasing the weight would improve the performance. And everything is happening so that I can reach to a direction where ultimately the overall error at the output can be decreased. And the overall error at the output is nothing but the combination of the contributions of error being made by multiple weights, right? Little bit of understanding, did you get, everyone? You might not get too much of understanding, but so that is what, I mean, differential function does in neural network, right? This is how you can, little bit of understanding I can give you at this stage, why derivative would matter, right? Suppose there's a loss function LW means that how I would define. So suppose I defined one of the loss functions like this, if you remember, and square. So if I say this, I told this, sorry, I just wait. I did something like this, right? If you remember this? This was one of the error function I gave you, right? Isn't it? I gave you this one. This is one kind of loss function. There can be million different kind of loss function like to this. Now this loss function is derivable, right? I can derive it, and everyone knows, right? So this loss function would be if I'm using, what are the parameters? I would be using weights, I might be using bias, right? So these are the adjustable parameters, right? So what I'll do, what I can get is, so if this derivable value is positive, this one, that is a loss with respect to the weights, the change in loss with respect to change in weights, That is what I want to calculate. So if this quantity is positive, that means eventually I would be doing is what I would be decreasing the weights. That means this derivable function is positive and I can decrease the weights, right? If it is negative, I would increase the weights. So these are the understanding that I would get through derivable functions, and that is what I wanted, because I wanted to understand that which move in which direction I have to increase the weights, what I have to do the with the weights. So this understanding is required. Okay. And so without derivatives, in a way, this update to the weight values or the parameters bias values would become impossible. So that's the only thing I can tell you at this stage of time, right? So don't worry, we would have this understanding little bit when we would start doing gradient descent in much greater details, right? So at this stage, this thought process was enough. Um, Now what I'll do is we'll pick up the next session, that was in the session 3. Yeah, session 3, and would start talking about something called we still have about 15-20 minutes, right? So we would be able to do a little bit of things. So the what is the overall thought process in this particular session that we'll talk? So we would talk about how to use simple neural networks. These neural networks would be simple, not very typical neural networks, to solve linear regression problems, right? And then we would use this to solve simple classification problems also, right? And once we would learn to do these things, then only we would take up some higher networks, which we normally call as a feed forward back propagation network, where we would actually learn that how a typical neural network with multiple layers learn, and how the error gets propagated, back propagated, right? You got this? So this is the overall thought process as per the syllabus. So I have made this a particular slide a little different from what is given. So a lot of examples I have inserted so that you can correlate with these examples very nicely. Otherwise, no, a lot of mathematics and thought process you tend to differ from the understanding. So I've taken a typical problem, which is I hope everyone would be able to understand very nicely. So the small data set I've taken, a very small now taxi services, service charges, for example, where we have the base fare and the distance traveled, right? So obviously, in typical scenarios, I would be given these kind of problems, obviously, and this is a typical linear problem, linear regression problem. So I want it. So based on my distance travel, I want to predict what these fare, right? So input and x output is clear with us. So x is the input, y is the output. I hope no issues in terms of understanding and visibility of the problem. Everyone knows about linear regression a little bit, right? So and we would be using gradient descent. You may not understand much, but you should be able to at least understand the idea. And there's the reason I covered little bit of what I covered in the previous slide. So how would I model it through neural network? That's the thought process, right? So what I need to do is obviously I gave a model, right? I would use a single perceptron model at this stage of time, for example, to solve this kind of problem, because there's only one variable x on the basis of which I have to do a prediction. So this is the kind of model I can use. What x can be over here? Anyone? X can be what? X can be
Input,
one of the
input,
Distance.
parameters,
parameters.
that is distance. I can take this
Distance
as an
feature.
x. Yeah, right. So this would, and w would be what? Would be per kilometer rate,
Per
right?
kilometer.
Right. Yeah. Base fare, it is up to us, because if I want to make it realistic, so there would be some kind of base fare also. A person is sitting in a taxi, there would be always kind of base fare. So I mean, I've taken this example very जानबूझ के मैंने इसको B लिया हुआ है because B would give you a kind of importance of the bias value. So this B becomes a bias value because it's a base fare, although it has nothing to do with my feature which is given to me, that is the X. You got my point? So I can take B as a bias value, as a base fare, which would be always there. You got this? So base fare. So we would include this bias by using the this augmented input. I can explain this, I know, and this would be bias value. I do not need to treat it as an input because see this would always remain one. So only this value would matter. So this bias value would matter only, right? And would be part of all the calculations, right? Uh, Now this is a step one. So what I'm trying to show over here is that given a set of problem which is in the form of data set, you would always get how I would set up a simple neural network, right? So step one, this kind of understanding is something which is required. So by considering that I had only one input, no, I and this and if assuming that there is a linear relationship between this. So someone might ask you, so why you came up with this only function? Because I'm assuming that there might be some kind of, I just want to test whether there is a linear relationship between these two factors or not. It may happen that there may not be a linear relationship, but if I'm trying to get a linear relationship between these two, I would test with a linear function, isn't it? That's how I do in machine learning also. I hope I'm clear on this factor, right? So now, step two would be what? I would define a loss function, right? I'll define some kind of function because I'll go with the training part. So I need a loss function. These are typical, very popular loss function. And when I would explain these loss functions later on, so I would take up an aspect of this, that what are the different kind of loss functions exist. So some loss function may be useful in some scenario, some other loss functions may be useful in another scenario. But in a very simple scenario like this, or khaskar, I mean, in linear regression, if you have done a little bit of machine learning, so mean squared error is a very popular function. I hope some of you might have done also, right? So where this is what the output function that I would execute, and this is the target value, right? So yi is the target value. This is the model, the linear model that I have developed. No issues on this, right? Yeah, understood. So now the step three would be the gradient, right? So do not get bugged up with that how this gradient is working. I'll explain that later on, right? I just wanted to, because see, I was not otherwise able to get that correlation between your understanding and what I want to explain, because explaining the gradient descent would require the switching over to the back propagation neural network, right? So the gradient I want, so I mean, just understand that what are the two parameters that can change over here? Anyone? Ultimately, there would be a one parameter only that would change. One is the weight vector. Base fare would always remain same. But this loss that I would calculate, and when I would be able to calculate this loss or an error, whatever, I would like to see when I would try to back propagate this error, and in order to update my weight values, that what is the effect of this total mean square error with respect to the change in the bias, and then eventually with respect to the change in W. Is it worth understanding it? So this definition is what? Rate of change of, to what proportion or to what manner L would behave, or the loss would behave with the rate of change in the bias. Okay. So what is the contribution of bias? You understanding this? Bias would have a contribution towards error. Weight eventually would also have a contribution towards the error. So, but In what manner? In what factor? So rate of change of W with respect to rate of change of error, L, right? So we have taken what? We have taken the first order derivative of this. You know, I think this is very clear. This is the first order derivative of these functions. Not an issue. Simple mathematics. Now, step 4 would be I would do a gradient descent update. Gradient descent update means that I'll choose some kind of learning rate, right? Now I'm trying to do what? I'm trying to uh, do something called, if you remember that I spoke in when I'm doing a perceptron, that a learning rule. Learning rule is what? If you remember, learning rule is what? Learning
How
rule
much
is
part the
new
system
weight.
learning?
Yeah, new weight is equal to old weight, if you remember, plus change whatever function we did. If you remember, learning rate we used, then we used target value
Yeah,
into xi
X bar.
something this.
Yeah.
So in a simple perceptron, it was a simple one, right? Now I'm just updating this kind of thing with a little more, I would say, complex one. This function is a I would say differentiable function. This factor. So old weight, you see, this is the new learning algorithm that I've defined. Old weight, old learning, whatever, with this new minus of, I'll explain the context of minus also, right? This is the gradient descent. There are two things. There are ascent and there can be descent. So understand in a very simple way. I want to minimize my function. What function? Loss function. It is a very simple perspective because I want to minimize the error, right? Other could have been the case mathematically, I want to increase that function. So there are two scenarios, increasing the function, maximize the function, or minimize the function. Since I have to minimize the functions in a very simple sense, this minus is because of this, because I have to move towards the negative of the gradient in a direction so that I can minimize that function. So since my direction is reversed, therefore this minus is there, right? If I would have gone into the direction, a positive direction where I want to maximize that function, I would have used plus, right? This little bit of understanding I gave you, but this should be good enough, right? So that is the reason why this minus is there. So old weight minus of the learning rate, which I've gave you the explanation why learning rate is there. And what is the rate of change of L with respect to weight? And this would happen in small steps, right? For every weight, wherever different kind of weights are allowed or weights are there in my network, every weight would be calculated with respect to the total loss that I have shown. So everyone would be contributing. You getting a little bit of an idea? So that is what I wanted to do. So gradient descent updates, we call it, right? So we can now we have done the setup for this small problem that we have with us, and I can show this with few kind of epochs, which so at the beginning I can take these weights. So these are the initial things that I can do. No, I think there's no issue on that. I can always pick up any. So in real world, it would not be 0 and 0 because it is weights and bias cannot be 0. Just one example, right? So what would happen? I'm using this function, no issues. So what would happen is that this would result in this value. Any issues on this? Because my weight and b is 0, and you know how this function is applied. So this would result in 0. Any issues on this? And these are how many values for all the input values. How many values I had? 5 values. So I'm talking about this, all the 5 rows. So for all the 5 rows would result in, so the first, you can say 0th iteration or whatever, it would result in 0, 0, 0. Any issues till now? Yeah, you getting my point?
Yes, sir.
Otherwise, if I am not going to explain it with an example, now I would find it very difficult to explain you that thought process of neural network, because now it is not the machine learning which is working. It is the neural network. Now, typical other kind of algorithms are not working. I'm to use neural network over here. So that's the reason I took an example. Now, I'll do the computation of the errors. So obviously this is the major term. Squaring to मैं कर ही लूंगा. I'll do a square later on. So I had this xi. I had the yi in front of me. I had this yi is what? Yi is what over here? The target value. Target value. This is what I have calculated. This is the value which I've calculated, and recently I've told you this is 0, 0, 0. Then I did the error calculation, which is obviously all the things would become negative. I would do what? Square of it also. You can do it in the same table. So I would calculate the square. Now, can anyone give me a little bit of an idea why and how this square is helping us? Anyone? How this square is helping us? This is a perfect case to talk about squaring. Exactly. So how this removal of negative thought process or negative values would help? Why I would like to remove this negative values?
Because we are more
Any
concerned with the value, not the direction here.
any more addition to that thought process? Anyone? You must have done linear regression by now, I suppose, in your network. Sorry, in anything more? Anything more convenient? See, in this particular case, because yi was all zero, therefore you saw negative in all the cases. But there could have been the scenario where you might have got something like this. For example, this could have been plus, and this could have been plus. You know, I mean, this could have come. Obviously, this kind of scenario would have been there, could be there. Agreed or not?
Yes, sir.
Agreed. So, what
Possible.
is now? Can you explain me why negative would, how it is hampering?
So it
Moving
will
the actual
Because
point.
yeah,
Negative
the
and
overall
35.
effect might, overall, because you cannot have overall effect of zero learning. Overall effect might be zero over here, but each and every value was significant for me. Each of the error was significant, but overall significant error was turned up into zero. So therefore, whether it is negative or positive, error is error. I have to deal all my errors with the same respect. So therefore, if I would have made it a positive, I mean square, and then I would have, see, if I've made it a square, what is the if I've done this, okay, but what is still the issue? What by squaring the error, what is the issue? One problem is solved, the negative sign, yeah,
So
anything?
variance and
No, any more thought?
so variance is
This,
increased between the
The values have
okay,
increased. So we
yes. In other words, you have changed the scale. Now you cannot
the
change the
scale,
scale.
yeah, we have feature scale
You
that.
have changed the scale, right? So you would do a square root of it later on, right? You must have used it, and root means square errors, right? So that is
Hmm.
where how you bring it back to the original scale, right? Because you cannot do a square directly, and so that we would do anyway. So that was not the part of this understanding right now. Okay. So now what I did is I computed the squared errors, and then what I did, you can see I did a sum of squared errors. No issues on this. This is the total squared errors that I've computed. Yeah, it's very easy. I hope
yep.
nothing I've done is a square. Now what I'll do is I'll compute the gradients also. You see, this is simple gradients I've defined. This was there. I have converted this into a simple, easier understanding. You can see, in a way, gradient is this only sum of all the errors. Here it is the multiplication with its respective inputs, right? So this was the weight, right? It might look like this, but this was a simple presentation. Now what I did is I introduced this term also, because these are the two important terms I needed. So I did EI and I did EI into XI also. Not an issue. I'll do what's, because I need a summation part. So I'll do a summation part also now. I'll do a summation also. I hope till now there's no rocket science I'm doing. So I did these two also. Now I have substituted and doing the calculations also. The gradient are being calculated. So I got what? Any issues till far? I think no issues till now.
Yes, sir.
Simple calculation that I'm doing, right? Now I'll put back. Now I would Now what I'm doing is I'm calculating the new bias and new W. So I'm put
Great.
back into the formula, right? I hope this is also not a rocket science I'm doing, right? I've just calculated this from here in the previous step. I knew the alpha. I took this value, initial value. That can be any learning rate I want, right? So what I got is, say, maybe after first iteration, what I got is these were the old values, gradient. I got a new value. Huh. That is important, right? What is happening? Can anyone tell me how it is similar to what we did in machine learning? What exactly is happening? Can anyone tell me? Can anyone tell me what is
The
happening?
new weights are decided.
So if suppose this was the original problem, I had three different kind of inputs, right? And I want to separate. It's a linear problem, I suppose. So maybe it's a regression problem. I guess it's not the classification problem. So actually, what is happening is, so in a 2D space, I'm trying to get many lines. Ultimately, I need to draw what? I have to draw a perfect regression line. No, that you can understand. Ultimately, what I'm trying to do is, I'm to get a perfect regression line, which is the perfect fit. Perfect fit on what? There have been many data points. I had 5 data points, but I can show my data points like this. So what I have to do, figure wise, I'll try many lines. You agree on this? I'll try with many lines. Why and how? Which line would be the perfect line for me? Anyone? Which regression line would be the perfect line on my data points? Anyone can
Minimum
tell me?
error.
More focused answer. Anyone? Minimum error. What? You're correct, but you need a more focused answer.
Loss function is
Which
also zero.
where the total error corresponding to every data point, and what was the total error was what? The mean squared error. Which was the function? The mean squared error. So the total mean squared function through all the data points could be minimized. Ultimately, loss function should have been minimized. So for every line that I would calculate, I need a line where that loss function of the total error could be minimized. So this line would have this error. This line would have been, we will calculate this error, right? So and after iteration one, what I did, let us see. So after epoch 0, we calculated these new values. So what I did is, this is the total error that I calculated. Initially, this MSC was what? Anyone? Initially, this MSC was what? I calculated
16.
something. This is the value I calculated. You got my point? Now, after one iteration of whatever I say, we calculated after epoch 0, right? This we calculated. So after epoch 0, this was the MSC that I calculated, and these are the weight and the bias I've calculated, right? Now, so this calculation is corresponding to kind of one regression line that I have developed. Agreed or not? Why? How? How I can say this? Why I said that this is equivalent to one line? What was the function? My function would have been what? Xi into, I would have written what? I would have written now
WX.
12.72x, because x is the input, I can control it, and bias. Bias is now
76.
2.76. It is nothing but a line equation where the MSA is a indication, total error indication. My target is what? What is my target? To minimize this MSC, isn't it? To minimize this MSC. So I would look for a line. Ideally, I would look for a line where this MSC could be 0. It is not possible. I would look for a line which has the minimum MSC. So next iteration I see. You see, same input. Now this is the equation that I just draw, right? Then I started calculating yi. No issues now. यहाँ पे कोई दिक्कत नहीं आ रही. No rocket science. I'm just putting these values. Which values? I'm inserting these values, right? I hope no issues.
Yeah.
This I
Yes, sir.
calculated this. no issues for all the values I did. So what I calculated is new values of these two terms. Then what I did is I calculated the gradients, the same process, right? Then I calculated the new parameters now. So previously it was different, previously it was different. Then MSC I calculate again. Now see what happened. Earlier it was what? Earlier the MSC was what? In five figures, 23220. Now the error is in four figures, 9380, 86, whatever. So what I shifted is I shifted, I minimized the error, right? Still, so this particular thing with this new values, this is previously there was one line, now this is another line they have drawn. Agreed or not? This is another line that I've
Yeah.
drawn into my data points. This would continue into number of iterations. It might look like this. Agreed or not? It would look like this. So every line over here is equivalent to what? A line. Every row, so sorry. Every row would have been, and what I could see, this is an experimental phase. I could see what is happening with the MSC. Where should I stop now? Anyone? Where should I stop?
When
Any
consecutive
indication?
when consecutive
Yeah.
MSC values are close or same.
Yeah.
Close or
Yeah.
almost
Yeah.
not changing.
Almost
You know,
Yeah.
not change.
a,
Yes.
a smart
Pattern.
person would have picked up this data point also. Another point, another person might have
Yeah.
picked up this. Well, yeah, that is okay. There's hardly any difference. Another person would have picked up this data point also. Other person would have taken more iterations to see where actually it stops. Yeah. So he see that, yeah. See, if I would have picked up at this stage, a person would have picked up this stage. So technically, what is an issue I have created? What is it? What this is called actually? If by mistake a person who is smart enough, no, no, this is okay. I picked up this stage. So where I have stuck? This is called local optima. You got my point?
Yes, sir.
We will call this as a local optima, where if I would have taken a little bit more patience, I could see that after many iterations, whatever, I started receiving zero. So I would have picked up this data point very smartly because here the error got absolutely zero. And this was equivalent to suppose this, whatever might be, right? So this could be a global solution I would have reached. Okay. So these are also some of the aspects that later on we can talk about these. But I hope you would have appreciated that you got this little bit of understanding in whole soul manner that how the network got developed, right? Isn't it?
Yes,
Now
sir.
I can give you a task, similar kind of task. What I did is now I took only one feature. Is it? I took only one feature. Now I give you a task that I have two features now, income and depth, and based on which I have to do an approval or disapproval or reject. So you can click a picture of this, please. Because if I'm going to, yeah, you can click a picture of this and try to develop a solution. Whatever I've shown you in the previous slide, can it be easily programmed through a Python? Was anything was there anything which cannot have been programmed? It is a simple programming aspect. Everyone can do it, I hope. Still,
Yes.
I'll create a program for it. I haven't created a program, but it's a very simple program. There's no rocket science involved into it. You just need to, I mean, functions you have to write very smartly, and NumPy would do all these things very easily, right? So now, and we are still talking about regression right now, right? We solved one kind of regression with single variable. Now we can introduce another regression, although now we would end this session and we'll take up this particular problem now in the next iteration. But this is a kind of assignment to you, for example, right? And the same thought process now. It might do little bit more calculations. You agreeing my point? There would be introduction of what? W1, W2 at the most. We did only with one variable, right? Still no introduction of what? Still, I have not brought I mean, MLP, right? A single neural network problem can be. Why single? Because only weights have increased. Only two weights would have worked now, right? So I hope you would be able to solve this particular problem. Not an issue. You should be, right? Anyway,
Yeah.
we'll take up this next iteration. But I hope this would have given a very clear understanding of that how we solve a problem, a regression problem. So everything looks very similar to what we do in machine learning, right? Isn't it? Right.
Sir,
Okay.
one
Any?
question.
Yeah.
Yeah,
Yes.
yeah. You mentioned about the local optima, right?
Yeah. Yeah.
Yeah. So, why would I want to exit at the local optima? Because I saw the values were changing
Yeah.
by, let's say,
No.
one.
No. Yeah. I'll tell you. A
Yeah.
person might take that only these money epochs in the beginning only of the loop. I'll run it for 100 epochs only or 100 loops, 100
Okay.
iterations. That is a local optima. No. I didn't have that patience. I didn't want to go too many iterations. I want my make my system optimized. You know, don't you think
But in
people
that
do
case,
that?
yeah. But in that
Yeah.
case, the person hasn't really solved the problem, right?
Huh, that's what. No. And it may not be required also. That's a beauty point. It may not be required. See, my idea was to separate the data points. It was not to get the most optimal line. You understand my
Okay.
point?
Okay.
Isn't it? My question was to
Great.
get a good regression line. Sorry, no, it's not a classification. A good regression line that is able to solve most of my unknown inputs. If I'm able to do that, well, good enough, right? It may not be very sensitive,
Correct.
isn't it? So that's the
So the
thing.
idea is basically to get the minimum and the most useful or most close function, not the zero always.
You would need an optimization function. That's what we were talking about, right? So it depends the kind of scenario problem that you are solving, right? You might need a very sensitive regression line. You might be very, very sensitive to it. So it depends upon how you take that particular problem. You need a very sensitive line that because it affects your business too much, right? So obviously you would like to optimize that particular line in that case. So it all depends and what is the thought process behind it, right? So for learning purpose, obviously. So obviously, from a business perspective, a person would like to get optimized line if he's doing a sales and all those things. So he would need a perfect line in that particular case. Yeah. So I will stop sharing this. Sorry, sharing to hata diya maine. Stop recording this. I'll put this content and I hope you're able to find the contents